Next talk is by Frederick Madsen, and Frederick is going to tell us about functional array suites.
Hello, I'm Frederick, PhD student at the University of Copenhagen. And last year I went on my change of academic environment. I went to University of New South Wales in Sydney, and I worked with these guys on Accelerate. And the result of that is what I'm going to present here. Okay, so I also have one of my first slides about Accelerate. It's almost identical to the last talk, so I think I'm gonna go over it pretty quickly. So what is Accelerate? Well, it's a language embedded in Haskell that brings array programming to Haskell, and it brings high-performance array programming to Haskell. And it does that by means of data parallelism. So a lot of the performance comes from parallelism, and since the language is data parallel, it's pretty straightforward to compile and run these programs efficiently on parallel machines, such as GPUs. So there are a couple of backends. Accelerate is designed with multiple backends in mind, and the one we've been focusing on in our work has been the GPU backend, but it should apply to other backends as well, especially for SIMD backends, such as a GPU. So the core data type in Accelerate are these multidimensional arrays. So think matrices, vectors, and hyper-rectangular data in general. And the language is rank polymorphic. There is one restriction in Accelerate, and that is that we only allow regular arrays. So we do not allow arrays to be the sort of the entry type of arrays. So you can't have arrays of different sizes. They really have to be rectangular. And sort of related to this restriction, Accelerate doesn't currently support nested data parallelism, which turned out to be quite relevant for what we try to do here. So it sounds that Accelerate is already a pretty useful programming language, and it is, but there is a problem that I'll try to shed some light on here. So let's take a step back, and instead of thinking about Accelerate, let's think about how you map data parallelism in general to parallel machines. So if you think about data parallelism in terms of these implicit parallel loops, what you need to do in order to run them on a machine, you need to make them explicit, these parallel loops, right? For example, in CUDA, if you want to run a data parallel program on CUDA, you have to specify the kernel that runs, and then you have to run that on a grid, and that grid in the CUDA world is then your parallel loop that you have made explicit, right? What happens if your machine cannot support the size of the parallel loop you're trying to feed it? Well, then somehow the program has to be made less parallel in some sense. So in CUDA, this happens automatically for you behind the scenes. If you try to run a large grid, larger than you have cores in your GPU, it will schedule the grid in blocks. So in a sense, you have this, it does this for you. Yeah. So what really happens is, or what you really need is to, if you think about data parallelism in terms of loops at least, is you need to tile your data parallel, your parallel loops into two loops, an inner and outer one, and you have to make either one of them sequential, right? It's really up to you or up to the characteristics of your machine, which one should be the parallel one and which one should be the sequential one. It could also make the entire loop sequential, but you really don't want to do that because you want to have high performance, you want to have as much parallelism as possible, right? So as I said, CUDA does this for you at runtime. So really there is a sequential loop you could think of around a kernel that's been executed in these blocks that are the parallel loops. Okay. So Accelerate uses CUDA, and CUDA solves this problem. So what is the problem? Well, the actual problem is actually not the parallelism, but it's the data that the intermediate arrays that Accelerate use to communicate with, you could say. So if your program compiles to, let's say, 2 kernels, and the output of the first kernel is needed by as input to the second kernel, it has to manifest this entire array, no matter how much sequentialization happens behind the scene, right? And then the problem is that the size of these arrays are not reduced by the sequentialization. Sorry. What you really need, if you keep on thinking about parallelism as loops, you need to do some kind of loop fusion. And this is complicated by the fact that we also need loop tiling, right? Accelerate already does this to some degree, but it's a fragile transformation, I claim, that's susceptible to change. Loop fusion is a well-known technique. It's also well known that it's not always possible to fuse your program into one parallel loop, right? So you're going to have intermediate arrays, most likely in everything but the most simple programs. And it's not very clear to the programmer when his program is going to compile to one loop or when it's going to compile to two loops, right? A small change might change that. So the programmer, in order to write these programs, to be able to scale to very large input sizes, for example, he really has to understand the fusion system, which we think is unfortunate. So we're going to try to remedy this. And the way we're going to do this is by streaming. So what is streaming? 2 years ago at this very workshop, I presented this paper called Towards a Streaming Model for Nested Data Parallelism, which tried to solve the same problem actually in Nestle. So what this work tries to do is try to see if we can do the same for Accelerate. And we do that, we eliminate these intermediate arrays that are too big. We do that by instead of thinking of arrays, we think of streams. And then instead of array operations, we think of transducers that transforms these streams into other streams. So what's important here is that we don't just transduce one element at a time. We have to transduce the elements of the stream in chunks in order to get these parallel loops as well, so we get performance out of what we end up with. So we need some kind of notion of chunking. The streams have to operate on chunks, right? What then happens, or what we want to happen at least, is that these intermediate arrays goes away and we end up with buffers instead that sort of implements these streams. And we want them to be bounded to make sure that they don't grow to the size of the array they sort of represents, right? Because then we haven't done anything. And so what this means is that instead of having to do all this loop fusion and loop transformation stuff, now we have to worry about scheduling instead. So that's not necessarily better or easier to solve, right? Because it's just we just push the problem around basically. But it's not all bad, because what we can do when we think about streams instead of loops is that we can expose these primitives in the surface syntax, basically exposing the data flow model to the user. And this syntax is then restricted to only allow schedulable programs. So we sort of remove the magic from the compiler and allows the program to specify programs that he knows will schedule and not allocate these huge intermediate arrays. So that's the basic idea. And we called it sequences, is the terminology. In the surface language, it's called sequences. Okay, so let's go back to Accelerate. I have the exact same example as the last talk. This is a dot product in Accelerate. It looks almost exactly like you would write the dot product using lists in Haskell. So you note that almost everything here is overloaded by Accelerate's own primitive versions of these. First we zip the two input vectors, and then we fold it with plus. And you notice fold doesn't have a fold R or fold L here. That's of course because we want to execute it parallel, so there's no order in the way it's like specified in the way that fold L and fold R. So okay. And vector and scalar here are just type synonyms for this general array type, where array SHA, where SH is the shape, which basically just defines the dimensionality of the array, and A is the element type. So for a vector would be a vector of floats, it would be an array dimension 2 and then float. Okay, and you can think of ACK here as meaning this is an embedded array computation. I mean, it's something that will live on the GPU, basically. Or you can also think of it as an AST node in our embedded language. So to get a result back, you have to use this run function, which then computes the program you have and reads back the result to the host, at least when you use the GPU backend. Okay, so what we want to do, or how we want the program to look like if we want to allow this sequencing in the service syntax is something like this. It's almost the same. We're just using some different primitives here, and we change the types a bit here. What you should think of when you see this sec type constructor is that it's something that's not all there at once. It's something that's ephemeral and will be sequenced through the device. You can also think of it as an AST node for a sequence expression in this restricted syntax for sequences. The suffix e here in the basic primitive operations, that just means that it works on scalar sequences. So we have some more general variants of the same operations that I'll get back to later. And the whole point of having this is then that the programmer should know that this will be evaluated in batches behind the scenes. So even though he doesn't know the batch size, you could say, he should know that when you try to run this, he'll take 2 sequences as input, and the runtime system will then pick maybe 1,000 floats from the first one and 1,000 floats from the second one, zip that, and then fold it into an accumulator, and then pick the next 1,000. But he doesn't really necessarily know the actual number, because that might depend on the backend and want to be backend agnostic. Okay, so now I'll just go into depth with the different combinators we support. So how to construct something of type seq or sec. The easiest way is just to take an accelerate vector and convert it into a sequence using 2sec e. And the other way is to use stream deliverables. So this can be used for a number of different things. For example, if you read frames from your webcam or something like that, you can stream it into accelerate as an accelerate stream sequence like this. And we support laziness to some extent. I mean, you support it in the sense that you can supply infinite lists here, and if you don't try to reduce the resultant sequence, then it won't get stuck. So that's nice. Okay, so once you have manipulated your sequence, you want to get back into the accelerate. There are a couple of ways of doing that. Stream out is the equivalent of run for sequences. You can stream out a sequence, get back into Haskell. And this also supports laziness in some sense, although you don't know as user, because of this batching, you don't know how many elements will be forced at a time. You know it will be a productive sequence. So if you ask for the first element, it might compute the first 1,000 elements and then give you the first element, right? But if you ask for the second element after that, it will all be computed, so it won't try to compute it again. You can also manifest a sequence. So that's a way of getting back to accelerate from seq. You'll notice there's this type constraint arrays of A. This ensures basically that A cannot have a list type, so it has to be the result of a fold. The reason why folds don't just return arc is that we want to support multiple reductions or folds over the same sequence, and having it in seq means that we can ensure that there will be a single traversal and not multiple traversals, basically. So you can easily combine run and collect to get a run function you can think of for sequences, as shown here. Okay, so using these new operators, we can redefine dot products in terms of sequence dot product, like this. So now we still take 2 input vectors in ACK, and the first thing we do is to sequence them, and then we use these sequence combinators, and then finally we collect the result in the end. A couple of things to note here about the 2sec. First of all, the arguments are amendable for fusion. So if, let's say, you pass something as x's that is fusible, that might go in and fuse into the sequence expression, so you don't actually have to manifest input. That's nice. And the other thing is that if it's a host, if it lives on the host, like if it's a result of use, if you know Accelerate, then it will be transferred in chunks, so you don't manifest it there either. Okay. So we can do more than just work on scalar sequences, which I'll show now. 2sec_e is defined in terms of this more general operation, 2sec, which basically takes a division, and then you can slice. You can think of any array of any dimension, and all these full shape and slice shapes, they're just there to make sure that you don't mess up with the ranks. The division specifies how you want to slice your array, and I think it's easiest to understand through example. So let's say you have a 2D matrix up here. There are 4 ways you can slice a matrix. You can do the sort of trivial thing where you just say, well, I just want the matrix, and say you want all in each dimension. You get the resulting like this. Then you can slice it like streaming the columns or streaming the rows using these two, and then finally you can get all the elements like this. Okay. Maps are also have general variance. So the map and zip width are sort of similar, so I'm just going to explain map here. Here is the standard map of Accelerate. It just maps a scalar expression over an array. Here is the sequence version, which maps any array function over a sequence. So this is a very general and powerful operation that we support. And then you can see how mapsec_e is just defined in terms of combining map and mapsec here. Okay, so using these, we can now show you a more complicated example. This is matrix vector multiplication using sequences. What we do here is we take a matrix and then we stream the rows using 2seq with this division. And then we can actually map dot product defined earlier, whichever one you want to map, over this sequence of rows. So this is actually an instance of nested data parallelism, which we had to deal with. From sec just manifests a sequence of scalars into a vector. Okay, so how did we implement this? Basically, what we do is we generate a directed acyclic graph of these transducers as internal nodes and consumers as the leaves, and the edges are then these buffers that yeah. And how you execute it? Well, there's always a purely sequential schedule for these stacks where you just compute one array at a time of a sequence. It's simple, but it's horribly inefficient, especially for CUDA, so we want to do better than that. We want to do chunking. And there are a couple of challenges there that we solved for maps. We solved it by vectorization, and for reductions, we solved it by having a special primitive that can handle that. I'll get back to that in a second. And there's also a matter of how we choose the chunk size. So we use a size analysis basically, and then we use a magic constant for your backend that defines what the chunk size should be for scalars, and then we find the chunk size that should be for the arrays of the size that you have in your sequence. Okay, so vectorization. We use Blalock's lifting transform from Nestle, but we generalize it to multidimensional arrays. So if you have an array function like this, the lifted version has this type, where you add a dimension basically on everything. That's nice, but we might introduce irregularity. Let's say you have the iota function, which takes a scalar and produces a vector from 0 to that scalar n. If you lift that, then you're going to get a matrix where the rows have different sizes. So you could try to make it rectangular, but it might be horribly inefficient. So we just disallow that for now. So that's future work. We only try to do chunking if we know the sequences are regular. Okay, this folding function. Fold stack flatten is how we implement folds. And this is our primitive for folding, our only primitive. And it is designed to be agnostic as to how many elements you try to fold at a time. This is basically just a fold L function. It will be executed sequentially. But what you need to notice here is that it can fold a sequence of arrays of any shape, but it only accepts a vector, so it sort of flattens the input element, and then it applies this folding function. And then we require this, which is semi-associativity, meaning that you must be able to concatenate vectors as much as you want, and it should give the same result. And this means we can also fold chunks, just as you would fold one element at a time, just by flattening again. Here you can see how fold-sig is defined in terms of this fold-sig flatten. It just takes the accumulator and the chunk values, and then it just folds the chunk values and use this accumulator as the sort of zero element. It doesn't have to be the neutral element in Accelerate, so we can do that, and that's nice, and we just use that zero element or as the initial accumulator. Okay, so let's see how we did. We did some benchmarks, some very simple ones, just to ensure two things. Basically, is that we haven't created something that's much slower than the ordinary Accelerate without sequences, and we can run larger inputs than Accelerate. That's the two goals of this. So we compare ourselves to Accelerate, and these are the specs. First, this is the dot product I showed you, with different sort of ideal chunk sizes for scalar sequences you can think of. The input are vectors of 1 million floats that we try to compute the dot product of. Here you see our sequence implementation, and here you see ordinary Accelerate implementation without sequences. And you can see once we hit a chunk size of roughly 16 million floats, we have more or less the same performance. So this will indicate that this is probably a good number for the magic number we need to find for our particular backend. And our particular backend has 5 gigabytes of memory, so that would allow us to have hundreds of streams live at a time, so that's good. Okay, so just to see that we scale, so we try to increase the input size, and we see that Accelerate runs out of memory here, but we just move on. This bit here has something to do with running out of host memory, actually. So I'm not entirely sure what's going on, but it should, in theory, just keep on scaling if we had enough host memory. Matrix vector multiplication, just to show you an example using this nested data parallelism. You see that we're not terribly slower than Accelerate, so that's good. It's almost the same, basically. And just to show you a real-world example or more complicated benchmark, this is a password recovery by looking up in a dictionary of words and using MD5 hashing. We also compare well with Accelerate here. This bit up here is the CPU Linux tool Hashcat. That's also good, and it also scales in the same way as .prac did, so that's also good. Okay, so just to summarize, here are the GitHub repos. They're still in somewhat experimental state, so you have been warned. Some future work. We want to get this irregular chunking right. We know how to do the lifting with irregular chunks, basically. We just need to figure out how to do the scheduling and picking the chunk size. We want to have scan. We have a scan, but it's horribly inefficient. We might want to infer these sequence annotations or sequence syntax because I might want to do that. There are some performance improvements like overlapping transfer and computation and multiple GPU support, like the last talk. Our model might actually have some nice support for that. So, questions?
How you would deal with random access or neighbor access of an array?
So the question was how we do stencils over sequences and random access. Okay, so the short answer is we don't. But if you can map the stencil over a sequence. So if you have say a sequence of frames, you can do a stencil computation in each frame by mapping, and we then do the lifting transformation to
So I guess the buffer should cover at least some set of layers of that in the furthest direction of the
No, because you have boundary conditions for each element, right? So it doesn't. Yeah, I'm not sure. Maybe we can take it offline. Yeah.
More questions?
Actually, pushing on the stencil thing a little farther, how expensive is it to just drop the first element and get a separate version of the stream like that, drop the first two, so you have a few time-shifted versions of that stream?
Good question. The question was how expensive it is to do time shifting of sequences. The answer is that we don't support that right now. They all run in lockstep, you could say. We have had some discussions of how to add this functionality. I'm not quite sure how it would look like. I could imagine that you could push an element in front of a sequence actually, and thereby sort of time shifting all other sequences backwards, and that should be doable by having like buffering one element, right? Might be reasonably efficient, but we haven't quite discussed that. Yeah, this yet.